Welcome to the demonstration of the engineering physics lab. The experiment that we are going to demonstrate today is called the Halleffect. So today we are having a demonstration on the Halleffect, and in front of you on the board what has been drawn is a schematic representation of the quasi 2D geometry that is required for performing the Halleffect experiment. By quasi 2D, what we mean is we have a two-dimensional slab with a very small third dimension. The sample dimensions in this diagram have been indicated as length is L, the width is W, and the small thickness is T. To set up Halleffect in the sample, we first need to drive current to the sample, which has been achieved by connecting it to an external battery, which is driving a certain current I through this Hall sample. To realize why Halleffect happens, we have to understand the concept of Lorentz force, which is nothing but the deflection of charged particles which are moving under the influence of a magnetic field. So in this configuration, there is a perpendicular magnetic field which is acting along this direction, and for clarity of understanding, the diagram of the coordinate system has been shown here. Right-handed Cartesian coordinate system, x, y and z, and in this notation the velocity of the holes, suppose this is a p-type semiconductor, the majority charge carriers are holes, and the holes will be moving in the direction of the electric field, so which is indicated by Vd vector over here. So in this Cartesian coordinate representation, the drift velocity is Vd is equal to scalar Vd times x cap, which is a unit vector along the x direction, and the magnetic field is perpendicular to the sample, which is magnitude of the magnetic field times z cap. So the Lorentz force will be given by Q V cross B, and in this notation it is easy to show once you substitute these values that it will come as minus E Vdb times y cap. So what this means is that if you are looking at holes and the movement of holes in a p-type semiconductor, the holes will be deflected towards minus y cap, which means in this notation it will be deflected towards the front face of this Hall slab. Now, just for sake of completeness, let us assume that instead of a p-type semiconductor, we have an n-type semiconductor. So will things change dramatically? We can find out by using the same notation that now the velocity of the electrons, the drift velocity, is along minus x cap. So it's written as minus Vd times x cap. The direction of B is unchanged. Magnetic field is in the same direction. And in the same way, you can show that the Lorentz force acting on electrons is also minus E Vdb times y cap. So the summary of these two equations is that both the holes and the electrons in a p-type and an n-type semiconductor will be deflected towards the front face of the Hall slab. However, as the sign of the electrons and the holes are opposite, the sign of the Hall voltage will also be opposite for the two cases. Now, this is the basic concept that is involved in Halleffect. Using this concept, we will quickly show how to derive the equation that is required for this particular experiment. So the first equation that one requires for understanding this experiment is the condition of dynamical equilibrium. What is meant by dynamical equilibrium is, because of magnetic field, these moving charges are getting deflected towards the front. However, this process will not continue indefinitely. After some time, when a sufficient amount of charge has been accumulated over here, these charges will try to oppose the further advancement of these same species of charges, because like charges repel. So for example, if the holes are sitting here, it will not like further holes to come and sit on top of them. So it will start repelling. And there will be a point where the repulsion because of the holes will be equal to the force that is felt by these holes due to the Lorentz force. So this is the condition of dynamical equilibrium. What will happen? What will happen is that in spite of feeling the force due to Lorentz force, in spite of wanting to deflect towards the front face, the holes will be unable to deflect, and it will be in sort of pseudo-equilibrium condition. So that is the condition for dynamical equilibrium, which is simply stated as the force experienced due to the Hall field or the Hall voltage is the charge times the Hall field, which is E times EH, where EH is the Hall field that has been generated because of the accumulation of charges on this side and no accumulation of charges on that side. Whereas the Lorentz force is, magnitude of the Lorentz force is simply given there as E Vd times V. I have taken out the minus sign because this is just a scalar equation. It's not a vectorial equation. I am not bothered about the components. I am simply writing down the magnitude. So, if I cancel E from both sides, I can show that the Hall field EH, which is nothing but the gradient of VH, that is VH is the Hall voltage, and so VH by W will be EH. Please look at this notation. W is the thickness, so VH is the Hall potential, VH by W is EH, which has been written here. So therefore VH is equal to VdB times W. But from classical free electron theory, we know that the current through the sample is simply given by this expression, where N is the carrier concentration of the electrons or holes, A is the cross-sectional area that the electron or hole sees as it goes through the sample. So in this case, A is nothing but W times T, because the electrons or holes will be moving along this direction, and you will see the area which is perpendicular to the direction, which is nothing but W times T. So rectangular cross section is W times T. So if I substitute all those expressions, I will land up with this equation, which I called equation 4, that VH is VI by NET. This is a very important equation for Halleffect. Now to derive Hall coefficient, which we require to do for this experiment, we need to remember the Hall coefficient is defined as the Hall field EH divided by the current density along the drift direction, which is Jx, times the magnetic field. So this is the definition of Hall coefficient, and simply by plugging in the values that I have already derived above, I can show very quickly that Hall coefficient is nothing but 1 by N times E, where N is the carrier concentration of the p-type or n-type semiconductor electrons or holes, and E is the charge of the electron or hole. So obviously this sign, if it is a p-type semiconductor, will be positive, because the charge of the hole is positive, and if it's an n-type semiconductor, this sign will be negative, because the charge of the electron is negative. So from this equation, we can show that 1 by Ne, which is the Hall coefficient, is nothing but, please look at this equation, 1 by Ne is Vh by V into T divided by I, and that is exactly what is been written here. This is equation 6. So this is the equation that we are going to use for performing this experiment. So now let us quickly come about the methodology of the experiment. There are two major parts of this experiment. The first part, which I call A, is basically the calibration of an electromagnet, because we are going to generate this magnetic field using electromagnet. So the calibration of the electromagnet will be done using something called a Gauss meter. We'll see how the electromagnet, how the Gauss meter looks like very soon. And once this calibration is done, this calibration basically means that for what current passed through the electromagnet, what magnetic field is being generated. Because as you know, the magnetic field in electromagnet is not permanent. It is generated or turned on because of passing of the current. So it is important to know for what current, how much magnetic field is being generated. That is the purpose of the first part. Once this is over, we will go to the main part of the experiment, which I call part B, where we use this electromagnet and a Hall sample to calculate VH by B, which is this important ratio, VH by B. The thickness will be provided to us, and the current through the Hall sample, which we will also call IC, will be something that we can calculate. We can tune that quantity. So now we are ready to go to the experiment. Let us continue with our demonstration of the Halleffect experiment. Before starting the demonstration, I would like you to look at all the separate equipments that are required to perform this experiment. In particular, let us start with this big white colored box, which is a constant current power supply. This is the apparatus that will be supplying current to the electromagnetic coil, which is located inside these two boxes, and it will be generating the magnetic field. So it is by tuning the current from this power supply that the magnetic field will be tuned. This is a digital Gauss meter through which we will be monitoring with the help of this sample. This, if you can see, focus on this part, you can see that there is a small red colored sample which is located inside this metallic cage. It is a very sensitive semiconducting sample, and this sample is what will allow us to detect the magnetic field that has been generated inside this electromagnet, and we will use the reading from that Gauss meter, which will be shown here on the digital Gauss meter, to calibrate the electromagnet. So this is going to be the first part of the experiment, which I called as part A of the experiment. I need to send current through the electromagnet and find out what is the corresponding magnetic field that has been generated. So keeping that in mind, I'll switch on the electromagnetic power supply, this constant current power supply, which is supplying current to the electromagnet. Now I will insert this sample, which is housed in this metallic cage, right inside this magnetic field, and I will lock it using this knob, and then I'll switch on the Gauss meter, and the Gauss meter reading should be the maximum. Why it should be the maximum? Because I know that when the magnetic field is passing from the north pole to the south pole, and if I keep my sample in a perpendicular condition to the magnetic field, if suppose the magnetic field is like this and I keep my sample perpendicular to the magnetic field, then the flux that is cutting through the sample will be maximum, and therefore maximum reading will be shown on the Gauss meter. So I want the sample to be perpendicular, and therefore I want this reading to be maximum. So keeping that in mind, I will first pass some small current through the electromagnet. So I am turning it to some non-zero value. I made it 0.2 for example, and this Gauss meter reading is showing 183. My job is to rotate this Gauss meter and see whether I can maximize the reading or not. So I am doing that, and indeed I find that when I rotate, 187 is the maximum, or 187 or 188 is the maximum value which it is showing. So this is around 191 it is showing now. So this 191 or 192, that value is the maximum value, and therefore this is the position at which the sample is exactly perpendicular to the magnetic field. So now in this configuration I will do the calibration of the electromagnet. So for doing the calibration, first I have to turn this external current to 0, and when I turn the external current to 0, I know that the magnetic field value also should come to 0. But because of the memory effects involved in an electromagnet, this value is not exactly showing 0 but some finite value. This is not required, and this has to be set to 0. The way I will set it to 0 is by turning this 0 adjust knob. Is written 0 ADJ, as in 0 adjust, and I will gently turn this knob and make it 0. Okay, so now I am ready to go for my first part of the experiment. The current through the electromagnet is 0, the corresponding magnetic field is also 0. Now I will take steps of some regular steady steps I will take. Let's say we will take steps of 0.25 amps. So when the current through the electromagnet is 0.25 amps, the Gauss meter is showing 238 Gauss, which I will note in my tabular column, and then the next value that is to be registered is 0.5, because I am going steps of 0.25. For 0.5 I am getting 474. As you can see, for 0.25 I got 238, for 0.5 I am getting 474, so roughly it's a linear trend, and this trend will continue as I keep on increasing the current. Next reading is 0.75. So like this linear trend is going to continue, and I am going to take the readings all the way till 4 amps. So in steps of 0.25 I will get 16 readings till 4 amps. So once this is done, at the end of this part A of the experiment, I know for what current, what magnetic field is going to be generated in the electromagnet. Now I am done with part 1. So I will again turn this current back to 0, and for part B of the experiment, what we have to do is we have to use this calibration that has been done to insert a sample the sample is pasted on this board here, and this sample will be inserted within the magnetic field in a perpendicular condition, and after setting up the connection in this box, which is called the Halleffect setup, we will be monitoring the Hall voltage that is generated across the breadth of this sample, as we have discussed before in the theoretical discussion. To do this experiment, let us understand the connectivity of this Hall sample first. So, as we pass current through the Hall sample, the current will be passing along the length of the sample, and if you focus carefully, you will see that plus and minus has been indicated along the length of the Hall sample. This is the length, and this is plus and this is minus. Whereas, as we have seen previously, the Hall voltage will be developed along the breadth of the sample, and these 2 points are basically terminals are collecting the voltage, the Hall voltage. They are used to measure the Hall voltage, and there are also some polarities indicated, plus and minus. If you look in terms of the wires, this red is for positive current, this black is for the negative current, this yellow is for the positive Hall voltage, and this green is for the negative Hall voltage. So simply by looking at the board and the wiring, we can figure out what wire has to be connected where. So now with this knowledge, let us connect the wires. As we have seen that yellow and green is for voltage. So I will first connect yellow to the positive of the voltage, green to the negative of the voltage, red to the positive of the current, and black to the negative of the current. So this is the Halleffect setup, and it can measure the current that is being passed to the Hall sample, and it has a toggle switch which can toggle between current and voltage. First, I will connect the sample, and which I have done, and now I will place the sample perpendicular to the magnetic field. So for that, I will attach the sample in the sample holder and keep the sample exactly in the middle of the magnetic field, pointing towards the North Pole. I will switch on the Halleffect setup. First, I will pass some current through the Hall sample. So for doing that, I will put the toggle switch into the current mode, and I will use the current adjust knob to pass some current. So here I am passing 0.9 milliamps. 0.9 milliamps is being passed. As you can see, the red LED next to milliamps is glowing. That means it is in the current mode right now. So 0.9 milliamps is perfect for me. Now I will use the toggle switch to go back to voltage. I will switch on the power supply to the electromagnet. Because the current to the electromagnet is 0, I know that the magnetic field also here is 0, and since the magnetic field is 0, according to the theory of Halleffect, the Hall voltage should also be 0. But as I can see very clearly, that Halleffect voltage is not showing 0 value, but some small negative value it is showing. This is an anomalous value that has to be removed, which we can do easily by turning the offset adjust knob. We will turn the offset adjust knob to set this non-zero value to 0. So now we are ready to start the part B of the experiment, where we are passing current through the electromagnet. For 0 current, the magnetic field is 0. For magnetic field 0, in spite of passing 0.9 milliamps current through the crystal, the Hall voltage is set to 0. So this is the starting point of part B of the experiment. Now we need to calculate VH by B. To get VH by B, for every magnetic field, I need to know the Hall voltage generated. But magnetic field will be generated by the current. So I will be turning the current knob here, electromagnetic box, this current, and through that the magnetic field will be generated, and because of magnetic field, Hall voltage will be generated. So let us do that now, and just to be careful, we will not take the same values step size that we took in the first part of the experiment, because we want to extract the magnetic field values graphically from the graph. Hence, we'll take a different step size. Let's say we'll step size of 0.3 amps. Previously we had taken 0.25, now we are taking 0.3 amps. So first, let us turn the knob. I set it to 0.3 amps. Yeah, so at 0.3 amps, I am getting 1 or 0.9, it's fluctuating here also, but it's around 1 millivolt I am getting. I'll note that down in the lab manual. And then next is 0.6. As you can see, for 0.3 I got 1, for 0.6 I am getting 2. So again, it's following a linear trend, which is expected from the theory. We know that VH is proportional to B. And we further can see that straight away, that because the sign of the Hall voltage is positive, the sample is a p-type sample. I did not know what is the type of sample before, but just by doing the experiment and setting it up, I know that it's a p-type sample. Had the sign been negative, I would have known it's an n-type sample. So this process I will continue till 3.9 amps. So I'll get 13 readings in steps of 0.3. 3.9 amps I will go, and I will come to the graphical plotting part of the experiment. So this experiment is over. Part A of the experiment has to be tabulated in table 1, and part B of the experiment has to be tabulated in table 2. However, in table 2, the magnetic field values have to be extracted graphically from table 1. And from the table 2, the slope of the VH versus B graph will be used for the final calculations.